Hello and welcome to this lesson on the structure and properties of diamond. In today's lesson, we will first define allotropes in order to understand the specific structure of diamond by examining its atomic arrangement. We will then move on to understand the unique properties of diamond that arise from its structure. And finally, we will explore some of the applications of diamond due to its properties. Allotropes are different forms of the same element, where the atoms are bonded together in distinct ways, resulting in different physical and chemical properties. A familiar example of allotropes is carbon, which can exist in several different forms. Did you know that the diamond used in jewelry and the graphite used in pencils are both forms of carbon? You may be surprised, since those two have very different properties. Graphite is soft and slippery, while diamond is extremely hard, but that is due to the way the carbon atoms are bonded. These differences in structure illustrate how the same element, carbon, can form materials with vastly different properties. We will examine the allotropes of carbon in this module, starting with diamond. To understand the structure and properties of diamond, let's dive deeper into its atomic structure and resulting characteristics. In diamond, each carbon atom forms 4 strong covalent bonds with neighboring carbon atoms. This bonding results in a 3-dimensional network structure, where each carbon atom is bonded to 4 others in a tetrahedral arrangement. This pattern repeats throughout the crystal, creating an extensive, interconnected lattice. Let's look at how this structure gives diamond particular properties. The first one is its hardness. The 3-dimensional covalent network structure of diamond makes it incredibly hard. Each carbon atom is held tightly in place by strong covalent bonds, making it difficult for the atoms to move. This hardness makes diamond the hardest natural material known, meaning it can scratch almost any other substance. It is used in drilling and cutting for this reason. Another property of diamond is its high melting and boiling point. To melt diamond, a tremendous amount of energy is required to break these numerous covalent bonds throughout the entire structure. As a result, diamond has an extremely high melting point of around 3,550 degrees Celsius. This makes it very stable at high temperatures. Diamond is also an electrical insulator. It does not conduct electricity. This is because there are no free electrons or ions in the diamond structure. All 4 outer electrons of each carbon atom are involved in covalent bonding, leaving no free electrons to carry a charge. The final property we're going to look at is diamond's thermal conductivity. Interestingly, diamond is a very good conductor of heat. The strong covalent bonds and the rigid lattice structure allow vibrations to travel quickly through the material, efficiently transferring heat. In fact, diamond is about 5 times more thermally conductive than silver, which is the most thermally conductive metal. Due to its unique properties, diamond is used in various industrial applications. Its hardness makes it ideal for cutting, grinding, and drilling tools. Diamond-tipped saws, drill bits, and grinding wheels are highly effective for working with hard materials like stone, concrete, and metals which would quickly wear down other types of cutting surfaces. Additionally, its exceptional thermal conductivity makes diamond an ideal material for use in high-performance heat sinks, which are devices used to dissipate heat away from electronic components, such as computer processors, to keep them cool and functioning properly. Diamond is also used in jewelry due to its shiny, reflective nature when polished. To sum up today's lesson, we delved into the structure, properties, and applications of diamond. We started off defining allotropes, different forms of the same element with different structures, and then delved into the specific structure of diamond. We discovered that each of its carbon atoms forms 4 strong covalent bonds with neighboring carbon atoms. We highlighted several key properties resulting from this structure. Diamond is incredibly hard due to its strong covalent bonds. It has a high melting and boiling point, as breaking these covalent bonds takes a lot of energy. It does not conduct electricity, as there are no free electrons or ions in its structure to carry an electrical charge. Finally, it is an excellent thermal conductor, as the strong bonds and rigid lattice allow vibrations to travel quickly, efficiently transferring heat. Additionally, we discussed the practical applications of diamond as cutting tools, heat sinks, which are devices that dissipate heat away from electronic components, and jewelry. By examining the atomic structure of diamond, we connected the specific microscopic arrangement of carbon atoms to the remarkable macroscopic properties we observe.